Physics builds its understanding of mechanical systems on a single, elegant foundation: simple harmonic motion. At its core, this is governed by a linear restoring force, described by a standard differential equation: mass times acceleration, plus a stiffness constant times displacement equals 0. But this mathematical baseline makes massive assumptions. It requires a perfectly frictionless environment and infinitely small displacements. It models a universe that does not actually exist. When we step out of that theoretical void and into physical reality, civil engineering structures interact chaotically with the environments around them. If we want to accurately model physical reality, we have to abandon the safety of this basic linear equation. True engineering requires us to systematically break the idealized linear oscillator. We have to mathematically force it to accept energy dissipation, external driving frequencies, and geometric nonlinearities. Conceptually, simple harmonic motion projects uniform circular motion into one dimension. This dynamic is represented algebraically using complex exponential notation. Adding a phase constant shifts the wave's starting position along the time axis, defining initial boundary conditions without altering the underlying physical frequency. Yet, even with these precise initial conditions, the mathematics describe a system that oscillates into infinity. That is an outcome strictly forbidden in physical space. Physical systems continually lose energy to their surrounding medium. We introduce this physical complication as a damping force, proportional and opposite to velocity. Adding this to our differential equation generates a new factor, an exponential decay envelope. This factor mathematically guarantees that the amplitude will gradually diminish, approaching 0 over time as the mechanical energy dissipates as heat. Before a system can decay, its baseline frequency is established by its stiffness constant, which depends entirely on material properties and physical dimensions. Looking at the experimental setup for a bungee cord drop, we can test this parameter. By varying the unstretched initial length of the cord and analyzing the total displacement of different attached masses, the data reveals a direct inverse relationship. The longer the initial cord, the lower the stiffness constant. Stiffness sets the natural frequency, and damping prevents infinite oscillation. But these static parameters alone cannot predict structural behavior when continuously injected with outside energy. To model an active environment, we add a periodic driving force. This creates forced harmonic motion. This introduces the risk of resonance, a specific, highly dangerous mechanical condition where the external driving frequency exactly matches the system's natural frequency. We can see the consequences of this mathematical phenomenon in the 2001 debut of the London Millennium Bridge. Structural models accounted for vertical oscillation. However, engineers neglected the lateral periodic forcing function from human strides. Pedestrians widened their stance to balance the lateral movement. Their steps created a positive feedback loop, matching and amplifying the bridge's natural lateral frequency. Achieving resonance causes unbounded mathematical growth. In the physical world, unless mitigated by a massive damping coefficient, this amplified energy will tear the structure apart. There is one final limitation to the idealized harmonic model, and it lies in the assumption of infinitesimal displacements. The universally taught pendulum equation relies on a linear approximation, assuming the sine of the angle equals the angle itself, which only works for tiny displacements. Error completely diverges past 7 degrees. Calculating the exact period requires integrating balanced kinetic and potential energy, yielding a complex elliptic integral. To bypass its vertical asymptote, researchers applied variable substitution and linear interpolation, producing an elegant, highly accurate logarithmic approximation. Geometric nonlinearity breaks standard textbook models. To map true physical behavior, physicists are forced to abandon linear approximations and rely on integration and interpolation. The simple harmonic oscillator is merely a mathematical ideal. It is a starting point, not a reflection of reality. To adapt this ideal to the real world, we must aggressively layer in the mechanics of energy dissipation, external cyclic forcing, and geometric limits. Introductory physics relies on elegant symmetry, but structural and mechanical engineering demands the dense, calculus-heavy integration of chaos. True engineering does not occur within the safety of the linear baseline. It exists strictly at the margins, where the simple models finally break down.